Okay, we're on the air. Live at the moment, but won't be live when you play it back. I'm going to talk more about the Fourier series, and then we're going to eventually be into the Fourier transform. But I wanted to just back up to what we were last doing with the pulse train, since this is definitely going to be on the quiz. You know, things with pulse train or the calculations of that problem number 1. But I just wanted to talk a little bit more about what we got by this formula. So when we went through the pulse train in this orientation, we come up with a coefficients formula. And gotta get my pen out here. What page am I on? I'm on page 228. So when you get all the way done, let's see, do I have a synopsis over here? Yeah. This is your formula. It's going to be on, I'm giving it to you on the quiz, so rest at ease. You'll have it right there in front of you when you need to do something with it. But this tells us everything we need to know about that particular orientation of the pulse train. So this was a custom formula in the sense that it assumed the pulse train had the pulses lining up at 0, going tau, t naught plus tau, etc. If all I wanted to do, though, is look at the magnitude line spectrum, notice what goes away. That e to the j term is gone because it's a complex sinusoid or complex exponential, so its magnitude is 1.
In the book that we have, the Fourier coefficient formula, instead of a tau at the end of the exponential, it shows t naught.
Yeah. That's right, and that's kind of you're getting right into the heart of the matter where I'm headed right now. So that's a good question.
Oh, thank you.
Is there something in particular that's annoying you about it?
I was just wondering, is that tau supposed to be there? Is it supposed to be t naught? Or?
Well, that's what I was going to try to show you. Okay. So in the book, I'll just take the advantage of being able to race electronically here. In the book, the pulse train is arbitrarily aligned. So that it starts at t naught, and then this is cap t naught plus little t naught. The amplitude is still a. And then what happens in this term in here, under that condition, then this had a different appearance to it. If you were looking in the book, this would be e to the minus j 2 pi then n f naught times little t naught, right? Is that right? Does everybody agree with that? There's a table of Fourier series coefficients. That's a very handy table. I have a similar table that I brought into my book, actually, too, because I think as users of this stuff, when you go back to grab stuff, especially those of you taking the lab, you want to go back and grab something, and where do you go to? I usually go to look in a table, and then if that doesn't satisfy me, then I have to wind my way into the detailed math to figure out what it is I really need to know. But does that sound reasonable? But when you're 5 years or 10 years away from this and you need it for something at work, you'll probably start in the table and say, I remember there was something, but then you'll look at the table and you'll probably say, I don't even know what this table means anymore. You might, you know. So you got to just work your way back to viability in terms of your skills. So that little t naught there in our particular application here took on t naught was equal to tau over 2, remember? Because we had it slid over so it started at 0. This became 0 and this became tau. We went through that last time. So if you plug in tau over 2 in place of little t naught up here, then you get the tau out in the backside, and then you get this factor of 2 cancels that 2 pi, so you just get the minus j pi. Does that clear that up? It's I smile about these things because it's so blasted detailed, right? Everything in the Fourier analysis is just like a little speck you're moving around with the tweezers to get every little piece of the math just right. Otherwise, it's not perfect. But the good news about the magnitude response is that doesn't matter. The time alignment doesn't matter. So I would say that this is the most important thing. This is the focus of one part of the quiz too. So thankfully, I'm on your side in that regard. I'm not wanting to go after every little speck of detail. The big deal is the sinc function controls the shape of the spectral lines, the way they have the humps to them from the sinc function, and the A is the amplitude, and the tau and the T naught, capital T naught, are the factors in there. The phase is kind of a whole nightmare unto itself, and I don't want to dwell on it a whole lot, but I just want to give you an idea of why does the phase have that interesting look to it, of sloping downhill and having jumps in it. Why does the phase have those jumps in it, for example? It's repeating. There's two things that go on though when you plot phase. Generally, when you think of complex numbers on the computer, like when you first learned about MATLAB, what did MATLAB do when you took the angle of a complex number? There's a special name for it. Can you remember from? Not convolution, just a property of complex numbers, angles in general. Remember something called the principal value? Okay. Well, complex number is on the unit circle, right? So the angle starts at 0, goes all the way around to 2 pi. Do you normally just go 4 pi, 6 pi, 8 pi? You put it in a principal value. So the principal value that normally is used in plotting angles is minus pi to plus pi, right? So when an angle drops down to minus pi or minus 180, then you just wrap it around and say it's back at the top again at plus 180, and so on. Remember that from somewhere. I don't know from where. So the phase is doing that. It's wrapping around. But then there's another thing that can happen to make the phase jump in this case, because there's two contributors to the angle in here, and that's probably about the last thing I want to say about this, because there's got to move on. There's two things that contribute to the angle in this expression. The sinc function contributes because it can change sign. So when the sinc function changes sign, you kick in a factor like plus or minus pi. So when sinc is positive, it contributes no angle shift, because a positive number has angle 0, right? Whereas a negative number is like 180 degrees of phase shift. It could be negative or positive. You have a choice because of that principal value idea again. We can wrap it to one side or the other. It's kind of like minus 180 and plus 180 is like the cut point back over. Well, I should draw it like this on the unit circle. If a complex number sits right here or sits over here, and this is real and imaginary, do you want to call the angle pi, or do you want to call the angle minus pi? It's the same point, so when it crosses through there, that's where it jumps, if you're doing the principal value. But on the sinc function, if the sinc is a negative value, it's like taking on a real number value sitting over in here, and you would write it as the positive number times an e to the j plus or minus pi. So that's what I've got circled right in here. These plus and minus pi's come from the sign changes on the sinc function, and I can just take my choice. I decided to plot it to make it look prettier, basically. But then there's a linear phase term that comes out of here. What's the angle that comes out of the e to the j? What's the angle of the complex exponential? It's just the argument itself. So that angle is equal to minus pi n f naught times tau. It's actually what I've got written right over here. And that's just rolling down. That's the downhill slope that you see in the phase plot. So the phase rolls down with that negative slope, minus pi n f naught, which is the harmonic frequency, n times the fundamental, and then tau impacts the slope as well. So that's rolling down, and that is causing the jumps to occur. But if the phase was steeper, well, whenever the sinc function jumps as well, then you get an extra kick of plus and minus pi. So this picture is actually not showing you the most complicated case. There's two things that can make the phase jump. One is just the linear slope coming down like this and needing to wrap by 2 pi, and then there's the other one that makes it wrap by pi. So I guess now that I'm looking at it, this does have the right stuff. Nowhere on this one do I see it wrapped by 2 pi though, which is kind of perplexing. Why is that? This wrap right here occurs when the sinc function changes sign. When the sinc changes sign, we have to kick in a plus or minus pi, and that's what's happening there. If we didn't have the sinc changing sign and we just had the phase slope eventually going through minus pi, then we should be wrapping all the way up to plus pi. And we don't have that in here because where that occurs is simultaneous with the sinc changing sign. So it doesn't have to happen because it never gets there. It just changes by pi because of the sinc is running behind this. If I was to draw it in there or look at it up above. Notice all those jumps are coincident where the sinc changes sign, because normally sinc would be right. Again, this is an example of something that's incredibly complicated for something that seems like it should be so easy, but the Fourier analysis just is like that. But the main focus by me, and the main focus definitely in the comm lab, is the magnitude only. Magnitude, I think, carries most of the information, and it gives you the important characteristics of the spectrum of the pulse train. Later on, when we talk about modulators, which maybe I'll get to the modulation theorem today, the fact that that spectrum is centered at 0, if we multiply, we'll learn that if we multiply the pulse train times a high frequency carrier, then we'll be placing this whole spectrum up on a high frequency. And so that's where one of the applications of the pulse train comes in, is in a simple radar system where you're just going to gate a high frequency carrier on and off with the pulse train. I'll say more about that when I get there, if I remember. Hopefully I'll remember. So another section I put in the notes, which I don't believe there's any talk on in the book, is suppose you have a complicated waveform and you don't want to try to do that Fourier integration to get the coefficients. In other words, you'd like to bail out on this calculation and say, I don't want to have to do that integral. It's common, right? You don't like doing integration? Or does everybody just love to integrate? When functions are complicated, you generally don't want to do it. And in some cases, you can't even find the integral in closed form, even in the thickest handbook. So people that use computers, and that's us, we know that numerical techniques exist, and this integral can be done numerically. Now, you haven't had a course in numerical methods, namely numerical integration, but when you first learn about integration in calculus, you look at these partitions, Remember, you break the integral up into a bunch of rectangular partitions, and then you look at adding those up, and then you take the limit as the width of the partitions goes to 0, and the delta x becomes dx, and all that other stuff. Remember that? Mm-hmm. So that's what I'm showing here. I don't really want to go through the details, but so the approximation can be made better and better by letting n become large. You can't let n go to infinity on the computer, but you can just let it become large enough so that you get a small approximation error. And something from digital signal processing that is not covered in 2610 and I don't believe is even covered in 3205 is the FFT, or the DFT. Because I don't teach 3205, I don't think it's in the curriculum, is it? Discrete Fourier transform?
Yeah, it is actually a little bit.
Okay, so you saw a little bit of the FFT then too.
Yeah.
Okay, because the FFT is just an efficient version of the DFT. Not to be confused with the Fourier transform of a sequence, which is different from the discrete Fourier transform. They're closely related, but the DFT is of a finite length sequence, and that's this definition you see right here. And it looks just like the approximation to get the Fourier coefficients, and that's what this line tells you. The bottom line, though, is on the next page, which just says, oh, if I can get the DFT of the sample values over one period, then I can just use MATLAB's FFT function to get those Fourier coefficients. And so I have some code in here that shows you how to do that. The main reason why I put it in here is just to show that you can resort to numerical methods and you can get satisfying answers. So I take a real practical example here of a finite rise and fall time pulse train. And what made me think about this, I think initially, was if you think about the clock in your notebook computer, it's running at over a gigahertz. What sort of harmonic content does it spray around the environment in terms of really high frequencies? It's not going to have a zero rise time square wave in it, for sure. It's going to have finite rise and fall. So I modeled it as a trapezoid. And this would be what you'd be up against if you wanted to do the Fourier coefficients for this. You'd have to do the Fourier coefficients integral over this waveform, which I know could be done because it's integrable functions. It's just kind of messy. I mean, we simplified the simple pulse train into a sinc function. So this could be simplified as well. As a matter of fact, once we go through the Fourier transform, we'll see that there's a way to get at this. And I'll just give a little hint on how you might get at it. This is kind of an interesting example of superposition, but this would conceivably become a complete triangle, right, if I did that? So one way of getting at this would be, that we'll have access to later, would be a big triangle and then subtract a littler triangle from it, which would be like, I guess you could call it beheading the triangle. Sounds kind of crude, but... And then this difference of those two Fourier coefficient sets would be the Fourier coefficient set for this trapezoid. But there'd be other ways too. But I put this in the computer and let it do it. And I don't really want to look at the code. I just want to develop some concept. So the first trapezoid, this is on a 1 second period, or a fundamental of 1 hertz. The first trapezoid has a nominal pulse width of 1/8 of a second. So that's from halfway up the rise and the fall. And then I let the rise time be 1/20th of a second. And there's the magnitude or amplitude spectra, line spectra. Notice it doesn't have the side lobes as strong as the full pulse train does. The pulse train would have had a bigger hump in here, meaning that there's stronger harmonics. The intuition that I want you to take away from this is that by slowing the edges down, in other words, making the rise and fall times much longer than the instantaneous, that reduces the spectral energy or the power in those side lobes of the line spectra. Now the idea behind that is when something jumps quickly, it produces lots of harmonics. When something jumps rather slowly in time, it's not able to produce as much harmonic content. Is that a reasonable intuition? Things happen quickly, lots of harmonics are generated, lots of high frequency content. Things happen more slowly, and it's more constrained. The limit would be like a sinusoid. A sinusoid just goes smoothly, and it only has a single spectral line, right at its fundamental. It has nothing else around it. So this is 1/20th, and then on the next page I slowed it down even more to 1/10 of a second, and now it's pretty much confined to just that main lobe in there, which still rolls off at about 1/8, 1 over tau, the nominal pulse width, because remember that's where the first null of the sync function is occurring, right where the 1 over the pulse width in frequency. It's a curiosity thing, but lets you know that if you slow the edges down, you slow down the harmonic generation, and that can be an advantage if you're trying to limit the amount of high frequency radiation from something too. But in terms of logic design, what happens if you slow the edges down? I don't know if this is something that you have in logic circuits or electronics, but if edges aren't fast, what does that mean from a timing accuracy standpoint? You have setup and hold times. You just have more uncertainty if you don't have nice fast edges, because if there's temperature changes or other things, when you cross the threshold, it's not as well defined if it's going over a slope as if it's going steeply up. It bangs over and there's no time uncertainty or minimal time uncertainty. So I don't think people that build Intel Pentiums and things want to have clocks that are too sluggish, because it probably gets into some timing issues with the devices. But then they have to seal things up better so it doesn't radiate as much stuff. It's pretty ridiculous actually these days how high a frequency the clocks are and how much junk radiates from your PC, and how they probably have to put shielding around the motherboard and things more and more as the clock frequencies have gone up.
So as far as having getting rid of your side lobes by having less steep rise and fall time.
Right.
From a communications perspective, does that make them easier to transmit, or does it really make much of a difference?
Well, that's a really good question. We're not going to send pulse trains. Yeah, it uses less bandwidth. That's a good observation. Remember, you're talking about spectral efficiency or regulations and sharing spectrum. This doesn't use as much spectrum. So yeah, that's something that has slower edges, and we'll look at pulse shaping perhaps, because that's actually in chapter 4 of the book. So that's true, and actually pulse shaping is used in all kinds of communications. It's used in cellular telephony to make sure that your neighboring signal, you could with Fourier transform theory, you could have another spectrum sitting in here. The very first simulation project, you're going to be doing some things like that, and you're going to be playing around with moving adjacent channels together, and I'll have you send some audio signals through, discretized audio, and you'll be listening for the interference and things that can be created if you try to pack things too closely in the spectral domain, and how that impacts the quality of the speech that comes out. Okay, here's the last little bit on the Fourier series that's really critical for working with Fourier series with the least amount of effort. What I mean by that is if the waveform has already been analyzed, like in the table that's in the book, how can you adapt an analysis from a known waveform to the particular waveform that you have? So this tells you, and this is a dual to theorems that are in the Fourier transform domain, it just tells you that if you know the Fourier coefficients for this signal x of t, and y of t has just been scaled by b and level shifted by a. I call this the level shift. What do the Fourier coefficients look like for y? The proof is down below, but it's you know, I've had 2 questions on this today. Is this really for real? And the answer is yes. The level shifting only impacts, this is the DC component, right? A only affects DC. And then on the harmonic components, for n not equal to 0, it's just whatever b happens to be that scales them. So that's how that second problem was worked out with the 2 pulse trains. Could be worked out using this.
Is that only the magnitude coefficients?
Now this is the whole
The
thing.
whole thing? Really? Okay.
Yeah, because in that second homework problem, b was equal to -1, so it flips. And when it plugs in down here, it flips the phase on everything by 180 degrees, because a -1 would be 180 degrees phase shift. You have to think when you're doing a magnitude plot, though, -1 is equal to 1 at an angle plus or minus pi. So if you're doing the magnitude, all you really care about is that. If you're doing the whole thing with the phase, then you have to throw the pi in there. So now let's do my little demo. And this is a challenge because I'm going to have ADS do an animation, and I'm running the video recorder, so I'm not positive. I think my computer survived this last year, but I don't remember. So Agilent ADS is Advanced Design System. We're using it in the Comm Lab. Some of you have had it in your RF and microwave classes from Dr. Song. It's available on the remote access computing system, and I have some zip packages on my website that have this lab experiment in here. So I've got everything in Lab 2, which is a spectral analysis lab. And I'm going to be looking at the pulse train. So there's my schematic. I'm going to open up the pulse train plot results right here. And what I'm going to do is, this is a very simple setup, but I'm using some macro functions for doing line spectra that are built into ADS. I'm doing a transient or time domain simulation. And I've got a pulse generator sitting in here, which is very similar to the pulse generator you'd have in SPICE or whatever circuit simulator. I can go down here and look at sources time domain, and I'm using not a current pulse, but a voltage pulse. I'm just probably not seeing where it's at in here. There it is. Yeah, it's right here, right? And if I was to double click on that, you can see all the parameters I get to specify into that source, just like in SPICE, right? You guys have used these things in a linear technology, or what's it called again? LT SPICE, yeah. This is just another variation on it, only it's the ADS version of it. So then I put a battery down here just so I'd have an extra knob to turn. And then I dropped in some variables on here so that I could actually have parameters that I could tune. And what I'm going to do is this tuning fork. If I want to run my simulation, the gear is what I press. That means simulate. But if I want to tune, and this is useful in microwave circuit design where you want to tune a microwave or RF circuit, just tweak a few parameters, but it'd be useful in anything, even in the lab if you're doing what you're going to use it for in the lab. So I set up my tuning already I already clicked on what I wanted to tune, and I got a couple of sliders in here. But if I didn't have this set up already, you'd have to go click on something in the schematic, like that variable, or maybe it might just be the impedance of a resistor. You can tune all kinds of different things. So I'm going to tune that. And I've got 2 sliders, one that's changing the duty cycle and the other one that's changing the offset that I'm adding to the waveform. So you can see there I'm just changing the duty cycle, right? And here I can raise and lower the waveform. So I want to leave it as the original pulse train, so I'll set it back to 0 is what I wanted to have it at. Set it to 0. I've got two line spectra plots. One is in dBm, which is like what you see in the spectrum analyzer in the lab, but it's maybe a little bit confusing to look at something in dB for a line spectra. So I've also got a linear one plotted up here, which is a little bit harder to see because if the lines get really tiny, you just don't see anything. I've got a marker on here that I can move around, and right now the frequency of my period is giving a fundamental of 10 kilohertz. So that's the fundamental. There's the DC line, and seems like it should be stronger than that. So I guess we have to think, why is that not stronger? This is a good quiz question too. It's not on the quiz, but it could have been. It's a little bit more involved. What happens when we go from a double-sided to a single-sided? Remember?
Half the amplitude.
Yeah, so if I'm displaying the single-sided,
Double.
everything's doubled, right? Except the DC doesn't get doubled. So I think it's perfectly correct on ADS's part to say that that is what it is. It's supposed to nominally be whatever the duty average value of the waveform is. And these guys are doubled because I'm folding the negative spectrum to the positive. Does that make sense? Mm-hmm. It looks to me like if these were halved, they'd be sitting, if that one right here was brought down to here, they'd be sitting kind of like you'd expect them to look for the two-sided. ADS doesn't do that because ADS is trying to emulate lab equipment. So they're trying to make this look like what you'd measure in the lab off a spectrum analyzer.
So generally for a double-sided spectrum, if there is a DC component, which will be larger than the other spectral components?
Not necessarily. That's what I'm about ready to do. I'm about ready to say, okay, how can I make that DC component go away? Right now, the average value of this waveform is what? It's the fraction of the time that it's on divided by the total time. So if I'm looking at 100 and it's on for, say, a tenth or whatever it is, it's going to be that fraction times the amplitude. That's the average value of the waveform. We didn't talk about that, but you learned about that at first in 2610. It's the X0 Fourier coefficient. You just integrate the waveform and divide by the period, and that's the average value. Remember that? It's not on the quiz, so don't worry. So what should I do if I wanted to make this waveform, this DC component, go to 0? I should be able to slide it down, say like that. So if the area of this piece in here above 0 is equal to the total area of the negative period, that will make the average value go to 0, right? Remember that? The average value is the integral of the waveform, so it's the area under the waveform. So I've got some positive area in here, and I've got negative area in here, and that's just going to affect the X0 value. Let's just see if I adjusted this about right. So I'll go look at the spectrum. It's pretty tiny over here, and just watch me if I tweak this up and down. And this is where the video is probably going to mess up on me, but it's going down, nulling it, and I go more negative, and it comes right back up again. Does that make sense? Because I'm now biasing the waveform too far negative, so now all this area is bigger than the positive area. Okay, what I'm going to do is I'm going to take that and just set that back to 0 again. And ADS, the new ADS, I hadn't played with this part of it, has this little refresh, so I can refresh the plot and have it rescale it. So now what I want to do is vary the duty cycle, just see how that changes. So I can change the duty cycle, I can make it look like a square wave, or really tiny. And in Lab 2, you play with pulse train. So I go look at the spectrum for that. This is where this part of in the linear scale it doesn't work so good, so I'm going to go to the dB scale here. as I get to be looking more like a square wave, I'm just going to have the harmonics spread pretty far apart. I don't have this set to go beyond 50% right now, I don't think. That's what it looks like, 50. So it's trying to approximate a square wave at this point. There we go. That's a square wave. On half the time, off half the time. So when you have it looking like a square wave, you're going to get the DC. I'm going to get a spike at the fundamental, and at the second harmonic, that one is nulled out. Remember, we were talking last time about odd half-wave symmetry? This is an example of a waveform that has odd half-wave symmetry. So the first null of the sinc function occurs right at the second harmonic, then the sinc function comes back up here at the third, nulls the fourth, comes up at the fifth, and so on. Go on the dB scale where it's easier to see, but maybe a little bit confusing. That is essentially 0. Minus 250 dB is like down there, tiny, tiny, tiny. But now as I bring the duty cycle smaller again, my nulls are starting to occur further out in frequency because my waveform is now moving off from being being a square wave. And there's other nulls that are trying to appear in here, I think, but they're not being discerned right now. There's a few more showing up. It'll start to look more like a sinc function, as I bring the duty cycle down even smaller. There, that looks a little bit more like a sinc function, right? I'm almost nulling those guys, and if I tune this a little bit, I'd probably get them perfectly nulled at that point. There's the pulse train. But what you have to imagine is the sinc function is coming down through here. The sinc function is going to go to 0 all right, but if it's not going to 0 where that harmonic is, it's not going to annihilate that one. It's probably going to 0 just right up in here or just down below here. Again, when you're in the lab, you'll see this really brilliantly as you turn a knob on the function generator and watch the nulls shift back and forth. This is just not quite as good, but it's not too bad. Is this making sense, or is this just looking like something that's confusing? And there's a sinc function shape there, and the null is moving back and forth because I'm changing tau, right? And 1 over tau is then shifting back and forth. 2 over tau is the next null, and so on, because that's the nature of the sinc function. And I can go move my marker out here and take a look. My fundamental was at 10 kilohertz, so what harmonic am I sitting on? The 18th harmonic, right? And if I could smooth my slider better, I could probably get that null to go just about to 0, but I don't really. There. There's a good setting. So I've got something down here, now just rescaled and covered it up. That's the 16th harmonic in this case. So that must mean that the duty cycle is 16%. So this is on 16% of the time and off the rest of the time. Seen enough?
It just doesn't look like 16%. It looks like smaller. 6%. Yeah.
Well, it's the 16th harmonic though, right? Well, we can see what the value, well, it says 6. Let's try to reason this out then. You're not believing me. I mean, I'm not wanting to have ADS lie to me, right? I don't see any other nulls out here, so that's the closest one. 160 kilohertz, that's 16 times 10. It's the frequency though is going to be 1 over that. So, is that right? I don't have a calculator on me. What's 1 over 6.39, for example?
0.156.
Okay, so 0.156 is kind of close to 16. I mean 160 kilohertz.
Okay.
So I guess I have the duty cycle off by a factor. It has to be 1 over that, so it's 1 over 16 is the duty cycle, which is the 6th then. So we figured this out by trial and error. That's what you do in the lab, right? Unfortunately, when you're taking a quiz, you don't get to turn knobs in anything until you start to make sense about what you're looking at. But if you've had practice somewhere, then hopefully that helps you out. Okay, now I got to turn off the tuner and shut this down. It's pretty cool though. This could have been constructed in Mathematica. In MATLAB you could have made a GUI for it, but I wanted to show it to you in ADS because I kind of like the looks of the line spectra. It looks kind of authentic to me. And if those of you that have used ADS before, I was cheating. I have a dongle, so I'm running it right on my laptop. I'm not running it on the remote access system. I couldn't tolerate that any latency, I don't think, in trying to get this to work well. Okay, now we're going to start looking at the Fourier transform. Believe it or not, the Fourier transform allows us to do virtually everything. I mean, right now we're looking at the Fourier series as a means of handling periodic signals, but we're going to see that the Fourier transform and the limit will allow us to include periodic signals within the framework of the Fourier transform, and then we'll have one spectral analysis technique for everything. Not that Fourier series go away, it's just we can have a framework that allows us to bring things under one heading, which makes for a little bit tighter math modeling. This is the definition of the Fourier transform. In the forward direction, it's an integral that involves, your aperiodic function x of t, and then you're weighted by an e to the minus j 2 pi ft. And when you want to leave the Fourier domain or the frequency domain, you put in the spectrum that you get, and you go back to the time domain. Now, one of the things that might bother you, and that's what this bullet states, but in my book, my editors made me put in an example of this bullet right here. How do we get to the Fourier transform from the Fourier series? You can actually do this by taking your pulse train as an example, and if you keep the pulse width fixed and then let the period go to infinity, all those periods will slide all to infinity, and it will look like, instead of having a series of pulses, you have just one isolated pulse. So as that happens, as T naught gets bigger for a fixed pulse width, what happens is the spectral lines get closer and closer together because the closest spacing is 1 over the period, right? So they get so dense that instead of being a line spectrum, it becomes a continuous spectrum. And that's kind of the magic of how you transition. And I refreshed my memory on that because they wanted me to do that too. What was the history of this guy, Joseph Fourier, and his contribution was Fourier series. People took that and converted it to Fourier transforms and all these other things, but he started with Fourier series. And if you're curious too, it was not an electrical engineering thing. In other words, a quote that I put in my book is, Fourier was not a signals and systems professor. He was a mathematician, but he was solving a mechanical engineering problem. He was solving for the temperature. He was solving the heat equation, which is a partial differential equation. He was solving for the temperature in a plate that is heated along one side, and wanted to know in 2 dimensions what the heat was in steady state, what the heat distribution is. So think of a metal plate like this book. You've got a heat source uniformly heating the edge of the plate. What is the temperature anywhere in this plate? I took partial differential equations when I was in grad school and used Fourier series to solve one and two dimensional problems. If you do EMAG, they're used for waveguide theory and other things, but I hadn't remembered that fact. I knew he was a mathematician, but I didn't remember that he was going after mechanical or heat transfer kind of a problem. Yeah.
Maybe, like, there's more than one definition of Fourier transform, so maybe this is it, but I guess I'm used to seeing like a 1 over 2 pi in front of the for the time domain.
Yeah, that's the alternate form. And in this book, we keep everything in frequency. So what you're used to seeing, and I forgot about that fact, you're used to seeing x of omega is 1 over 2 pi. Thanks for bringing that up, because I didn't remember. So the book that used it for 3205 does it omega domain transforms. Okay. Guess what? I like this one better because it's perfectly symmetrical, and I like hertz better than I do radians per second, because communications people deal with hertz, controls people deal with radians per second more. Or at least that's my view. But this one is nice and symmetrical looking. The only thing is you got to carry around this extra baggage of the 2 pi's. But other than that, you've got a nice symmetrical pair. Okay, so with that said, if you need to look up a Fourier transform pair, you're going to have to use the table in the appendix of this book and not use your 3205 book, because those are the omega domain ones. When I was writing a similar table in the book I'm working on, I put in 2 columns, one for F and one for omega, so that it'd be more universal for whoever, for the reader. But this is my preference, and this is where I do all the examples. So just think real frequency is F. So that the primary condition for the existence is that the energy, or the absolute area, I mean, of the signal being transformed is less than infinity. And obviously periodic signals don't meet that condition, but we're going to make an exception using this technique called Fourier transform in the limit. So once you are into the frequency domain, you have a continuous spectral representation for the signal, whereas the periodic signal is not a continuous spectral representation. It just has spectral lines in it at the harmonics. And we know that's the case because that's what Fourier series is all about. It says you just need to have spectral component at harmonics, not everywhere. But when you have a single isolated pulse, it becomes a continuous spectrum. So it has magnitude and phase. It has real and imaginary. Most of the time, we're dealing with the magnitude spectrum, which the slang terminology is amplitude, just like in the line spectra. And on occasions, we're dealing with the phase spectrum. There's some nice symmetry properties, just like we had for the Fourier coefficients. If the signal happens to be real, then the magnitude spectrum is always even and the phase spectrum is odd. And that carries over from the Fourier series idea, even magnitude and odd phase. Another thing that carries over from the Fourier series is that the signal itself is even. It's still real, but it's an even function. Then the imaginary part is 0. And if it's an odd function, then the real part is 0. Now there's another definition which we'll be using later on in the COM section, but right now we'll just look at it in the energy sense, not the power sense. But energy spectral density from this little development is defined as the magnitude squared. So I think that shows up. I don't know why I don't have it down here. Yeah, energy spectral density is this guy right here. Magnitude squared of the Fourier transform. And if you do the units check, it's volts second squared, and then that becomes, in a 1 ohm system, that becomes watt seconds. And watt seconds squared. And now you can, this is a little bit confusing, but watts per second is, or watt second is joules, right? So I have joules, and then I have the leftover seconds on the top, and if I shift that to the bottom, it becomes hertz, right? So it becomes joules per hertz. So then this equation here makes sense that if I go to integrate the energy spectral density, which has units of joules per hertz, and I'm integrating it in frequency, I'm going to get joules then. A density is usually some quantity, like, you know, a material has a certain density per cubic centimeter or something like that, and then you multiply by the volume, and then you've got what the mass of something is. Here it's the density in the spectral density. So that works out. Maybe you don't think that way, but like I was saying last week, thinking about units can catch you so many times from doing something foolish. You're not thinking, and you say, wait a minute, let me check my units, do they make sense? And you find out you're forgetting something. Okay, we're getting close to the quiz time, but not quite. So here's the definition. I knew I had it in here, I just didn't remember whether it was at the end or the beginning. G of F is what the book uses for energy spectral density. Okay, the fundamental signal to do a Fourier transform of is the rectangular pulse. So this is just a single pulse instead of a pulse train. So it's something centered on little t naught. So width tau, amplitude A. So you go through that integral. It's just finite duration signal. You go through the integral. It's kind of similar to the Fourier coefficient, except it's just a single pulse rather than a single period we have to integrate the pulse over. You get a sinc function. So this blue boxed equation is like one of the most fundamental of all Fourier transforms that you just sort of commit to memory as being useful for modeling and analysis, the basic sinc function model. And actually, the one that I remember is not with the T naught in there, because that gets handled with the delay theorem that comes up here. One that I remember is just simply pi rectangle over tau is just sinc is tau times the sinc of f tau. That's what I remember. Does anybody have, I guess because you used omega domain, you don't have this memorized then from ever before, because you've never seen it in this notation. So this has been an aha moment for me, because nobody last year told me that the book uses omega. So I was expecting too much. You had something equivalent to this, so probably, I don't know what it looked like. So tau sinc f tau. And then this is the spectrum and the phase. It's the continuous version of the line spectra for the pulse train. So it has this sinc function shape, only now it's continuous. The nulls are at multiples of 1 over tau. The phase has the sloping business from the tau naught. And if you draw it a particular way, like here, I picked a particular value of t naught, I think it was. Then you get this phase slope, and you get the wrapping and things like we were looking at before. It must be that I think I have t naught equaling, is it tau over 2 or tau over 4?
It says tau over 2 right there.
No, I'm just not, yeah. I make my pictures, but then I don't stare at them long enough to realize where I put the note in. And there's the energy spectral density. Then we go into a whole bunch of theorems after that. And I'm going to do 2 theorems, I guess. Superposition is just obvious from integration formulas, but I left a space in here to just show you how you would do that. Every transform that you've ever learned about has linearity that holds. So the way you'd end up proving it, though, is you just shove this whole thing inside the integral. So that thing slides inside of there, dt. And then you say, I'm used to using my calculus to integrate functions, and I know just the property of any integral is that I can factor constants out in front, and if I have a sum of two different functions, I can integrate the individual functions. So I'm skipping some steps here, but you just know that this is going to be a1 times the first integral, of x1, plus a2 times the integral of the second one, with the appropriate things in there. And then that just leads to that result right there. This is pretty much a no-brainer. As a matter of fact, I would venture to say that you would say this is a theorem without even looking at it in a book, because you'd say it must be true because of what I know about integration and calculus. You wouldn't question it. The second one is definitely powerful and popular. It's a little bit more involved to get to this one, but it's very powerful. This is basically similar to what we were looking at for the Fourier series, which makes me think there was another theorem on that page for Fourier series that I skipped over, and that was the time delay theorem. Just jump back for a second.
Yeah.
I did have it on there, right?
It's 237.
Yeah, it's right down here. So this just looks at what the Fourier series coefficients change by, and they pick up that phase shift factor when you have the t naught, which lets you know that time shifting a waveform doesn't alter the magnitude, because if you take the magnitude of these coefficients, you still get the same value, because that e to the j business becomes 1 when you take the magnitude. So in this little theorem here, though, again, you just start off with the definition. In the business of active learning, what I would do is I would stop and make you break up into groups and work it out, and then one person would raise their hand and tell the class how they did it. I'm not going to do that right now, but someday I'm going to try that, or have you do that. That's an active learning principle. It comes from School of Education, I guess. But what looks like a good thing to try here? Pardon me? Okay, a substitution, right? Okay, do you have a favorite letter you want to pick for the substitution? Okay, that's what I was going to pick. That's my favorite. So lambda, he said. So I'll let lambda equal t minus t naught. And as soon as I do that, then I can rearrange that and say t is equal to what? Lambda plus t naught. And then a few other housekeeping matters that you have to take care of when you do a change of variables in an integral. What about d lambda? D lambda is equal to what? dt. I don't have any problems with that, so I'm clear there. What about my limits? As t goes to plus infinity, what does lambda do? Plus infinity. As t goes to minus infinity, lambda goes to minus infinity. So I'm square on that. Remember those little details from calculus? Okay. So I can safely put my limits in. And then I have this e to the minus j 2 pi f of t, not t, but lambda plus t naught d lambda. But then I can do some factoring on this guy, break that apart. And when I break it apart, I'm just going to sort of throw it off to the side here. Times e to the minus j 2 pi f t naught, and That's outside the integral, right? Pull that outside the integral, and that way you know what you're left with in terms of lambda. You're going to be left with this guy here, and then that factor is what comes from the delay. I'm sure Dr. Trimboli went over this in the omega domain transforms. And then the dual of it, which we'll start off with next week, is complex sinusoid and frequency shifting, or frequency translation. We'll also look at duality again too, which tells you that this has to be true, because the Fourier transform pair being so symmetrical means you can look at this idea of duality. Time shifting gives you a complex phase. Frequency shifting gives you a complex sinusoid. I mean, there's a dual relationship. This I'll have to go to next week, but you see a similarity between that and that, right? I don't want to fry your brains out because I want you to work the quiz right now. Any questions before the quiz? Calculator, good. Eraser, good. Yeah.
Even better. Yeah.
No. If you want to have a scrap paper, that's fine, but you don't